755. 755. I have a spring on a table. This is x equals 0. That's when the spring would be relaxed. I extend the spring. I have an object here on this table, and the position of this object equals x. In fact, I bring it out as far as I possibly can so that when I let it go, that it doesn't go back. It's the maximum possible displacement that I can give this object. And the question now is, how far can I move it so that it doesn't start to slide? There is a static friction coefficient mu s, and there is a kinetic friction coefficient mu k. Let's put in let's make a free body diagram. mg, non-negotiable. Here is a force, the spring force, whose magnitude equals kx. It's opposing x, so I can write down in vectorial form that it is minus kx, but I'm only interested in the magnitude now. And then there is a normal force from this table. I said earlier that there is no friction. That, of course, is not true. The whole idea is that there is friction, as you can see. And as this object wants to go in this direction, the only way that this can be prevented is that there is friction here. The frictional force is exactly opposing this. And if these two cancel each other out, there will be no acceleration. The object, in this case, will stay put. Well, so the requirement is that the frictional force, F friction, the magnitude of the frictional force, as long as that is equal to kx, then the sum of all forces in the x direction will be 0. And I call this the x direction. Now, the frictional force is always less or equal to the normal force times the static friction coefficient. It's static because it has to start moving from 0 speed. Now, n equals mg, you see that immediately, so this equals mg times mu s. This is correct. And so the requirement then is that kx must be less or equal to mg times mu s. And so what do you find? That the maximum possible distance x, so that I can move this out so that it doesn't start to slide, equals mg times mu, that's a bad mu, but it is really a mu, divided by k. And so that's then my final result. And let's look at this result and see whether we can understand this qualitatively. The first thing is that if mu s were 0, notice that x maximum equals 0. That's immediately obvious. If there were no friction at all, there is no way you could move it to any distance, it starts to slide immediately. So the fact that it is linearly with mu s is quite pleasing. Suppose that k is very small, this is my way of saying it's very small, then the spring is very sloppy, so this force is small, and so it's immediately obvious that you can bring it out very far and still have equilibrium. So you can move it out very far, the spring is not very strong, and it will still stay put. It's also clear that if you increase the friction coefficient, so if you make the friction coefficient very high, also then you can bring it out much further so that it stays put and thus it doesn't slide back. I think we've hit this hard enough, and now I would like to go to the next part, and that is I give this one a teeny little push so that instantaneously I break loose this surface here, I break loose the contact, so my static friction coefficient will all of a sudden become the kinetic friction coefficient. And so this force, which was mg mu s, goes down. It becomes now mg mu k. And therefore, this spring force is stronger, and so the object will go to the left. And if I call this the positive direction of x, to the right, then I can write down the differential equation. Ma this of course is all in the x direction, would then be minus kx. This was this maximum position because that's where I started from. This is the spring force, opposing x, plus mg times mu k. Notice there is now a kinetic friction coefficient because the friction in this direction is reduced because I break loose the contact. And so this is the equation of motion, if you want to put it that way, and so that also equals minus mg times ks times mu s minus mu k. I just substitute in here for x max the value that we just calculated. And so the absolute, the magnitude of the acceleration, which is in the minus x direction, I want to remind you of that. The magnitude equals of a, m cancels, equals mu s times mu k times g. So that's the instantaneous acceleration once I break it loose. Now, when is the speed maximum? That is a very interesting question. So when is the speed a maximum? Here is that spring. Let this be the position x equals 0. This was the position x maximum. It starts to move, and there comes here a position x, and I will call that where f equals 0. Remember, when it starts to move, this spring force is larger than the frictional force because of this mu k being smaller than mu s. But as it moves to the left, the spring force goes down and down and down because the spring force is proportional to x. And so there comes a point here that these two forces cancel each other out. The object is no longer being accelerated, and so right here you must have reached your maximum speed. And so the maximum speed will be reached then when the spring force, F of s, the magnitude of the spring force, equals mu k times m times g. And we know that the spring force, the magnitude of the spring force, equals kx. So you find immediately that that will happen when x equals mu k, mu of k times mg divided by the spring constant k. And so earlier we had x maximum, we had a mu s here. Now we have an x, and we have a mu of k here. And so you can immediately see that this must be smaller than x maximum. It's immediately obvious because this mu of k is smaller than mu of s. So it's immediately obvious that this point where that will happen, where the speed reaches a maximum, is on the left side of the maximum displacement, where the object is still standing put. Now I want to ask you something extra, and that is, what is its maximum speed? This is not being asked, so you don't have to answer that question, but I thought it would be useful. What is the maximum speed? And now we're going to use the concept of energy. Keep in mind that when I release the object at its maximum displacement x max, there is potential energy in the spring, which is 1/2 kx squared. When it reaches that point where the force is 0, there is only this much left, F equals 0. So the potential energy was large, the potential energy is now smaller. The difference, however, is not 1/2 mv squared of the object. The reason is that there is friction, and the friction sucks energy out, and I must take that into account. So the loss of energy must be taken into account before I put this equal to 1/2 mv squared, which is the kinetic energy of that object. So I must now take out the energy that the friction takes out, that goes out in the form of heat. So you must subtract the frictional force times the distance that the frictional force moves, x at f equals 0. And you know what I mean by that. We just calculated that value. And this now, this is lost. This goes out in terms of heat. Notice the frictional force is in this direction. The object moves in this direction. That's why energy is being sucked out of the system. The dot product is negative. You see this minus sign here. And this now would be equal to 1/2 m times v maximum squared. It would be the kinetic energy right at the location x where the forces are 0. And if you massage that a little further, because you know what x max is, and you know what x is at f equals 0, you will find that the maximum speed that you reach at that location equals g. I hope I didn't make a mistake. Mu s minus mu k divided by the square root of m over k. And let's see whether we understand this result. It's always nice to do a few simple checks. Suppose mu s equals mu k. It's clear that if that's the case, that the object will never start moving. And you'll find indeed that Vmax equals 0. If you have a static friction coefficient, which were the same as the kinetic friction coefficient, if I just tap that object, it's standing still, right? Just standing still, hanging in there. And if I tap it, there is no change in the frictional force. And so there is still equilibrium between the spring force and the frictional force, so it's not going anywhere. And so if it's not going anywhere, it doesn't pick up any speed. So it is very pleasing that if the two are the same, that the maximum speed that you get is indeed 0. Let's now ask ourselves the question, where does the object come to a stop? And so I'm going to make the drawing again. This was the relaxed spring. And then here we have this point x where f equals 0. This is where the velocity, as we just calculated, reaches a maximum value. So I remind you of that, Vmax. And at this, and then further on here is the location x max, where we could put it without the object being moving, so the object would stay put there. Now, when the object is here, there is a frictional force which is maximum. It's always maximum because the object is moving. And there is the spring force in, the magnitude of the spring force is this kx, and this x is at this location where f equals 0. Now, from this moment in, it has a certain speed. This force becomes smaller and smaller and smaller, but this one stays the same, so the object is going to decelerate. And let's now ask the question, will it reach point x0, x equals 0, that is the position where the spring is relaxed, and what speed will it have? Let us assume that it will indeed reach that point, and let us assume that the velocity that it will have there equals v at x equals 0. Now follow me very closely. Forget this point here, I don't need that. I'm going to start here. Right here, in terms of energy, I have 1/2 m Vmax squared. That is at that location f equals 0. That's kinetic energy. I also have potential energy in the spring, which is 1/2 k x squared at that location f equals 0. When it reaches this point 0, it's not even clear that it will. This is not equivalent to 1/2 mv squared here because the frictional force takes energy out, as we just saw before. So I must subtract the work done, the negative work done by the frictional force, which is now from x f equals 0 to x equals 0, assuming that it makes it to that point. So x f equals 0. That is this distance. And this then would be 1/2 m v x equals 0 squared. And now the whole question is, if this is positive, then indeed it will make it and it will have a speed. If it is 0, it will come exactly to a halt there, and if it is less than 0, it won't even make it here, but it will come here to a position which I will call x stop, which will be on the right side of x equals 0. Well, we've calculated Vmax. We have calculated this location x, so you can substitute that in this equation. And we have in our problem that mu s equals 0.35 and mu k equals 0.25. And you substitute that in here. And what do you find? What did I find? I found that this was negative. And therefore it will not make it to x equals 0. It will stop short. Now, well, we'll go a little further. This is the kind of problem that could easily be asked at an exam. Where will it stop? I now want to know precisely the position where it stops. I know it's on the right side of x equals 0. It will stop here. What is that location? Again, energy considerations. 1/2 m v maximum squared at f equals 0 was the kinetic energy when it was here. The potential energy, 1/2 k x squared as f equals 0, is the potential energy here. And when it comes to a halt here, there is still potential energy left because the spring is still stretched. How much potential energy is there left? There is 1/2 k x at that position stop squared. Oh, there's a minus sign. Sorry. This is how much potential energy we have. This is how much there is left. So the difference is what is available in terms of energy. So this must be a minus sign. Now I have to also subtract the work done by this frictional force. So that is mu k times mg. And now it travels over this distance. So the distance is x at f equals 0 minus x stop. And this now is exactly the potential energy at the moment that it stops, and that is 0. So when all this energy has been consumed, so to speak, the object will come to a halt. Well, if you look very closely, you know all these things. The only thing you don't know is x stop. And so you have one equation with one unknown as x stop, and you can solve for x stop. What will be the situation when it comes to a halt? Here is x equals 0. Here is x stop, which we know is on the right side of x equals 0. At this moment, there will still be a spring force, and the spring force will be k times x stop. And so what now will be the situation with the frictional force? The frictional force, as it was coming in and it was decelerating this object, the frictional force was larger than the spring force. The moment, however, that it comes to the stop, instantaneously the frictional force will be exactly the spring force. So there is a sudden drop in the frictional force. And the frictional force becomes exactly kx stop. So as it comes in, the frictional force is larger than this one. It remains constant. And then, all of a sudden, when it comes to a halt, the frictional force goes bloop, adjusts itself so that it exactly cancels the kx stop. Friction is always a tricky thing. Friction can be lower than the maximum possible. Only when it is moving is the frictional force the maximum possible. It's not moving now. It stopped. So it immediately adjusts and it stays put. Just imagine that the frictional force remained larger than kx. Well, then the object would go back. Have you ever seen that? Have you ever seen an object that comes to a halt because of friction and that then all by itself goes back? Here, I have a little purse here for my coins. If I put that on here and I move it, this friction that brings it to a halt. Have you ever seen that it would come back all by itself? Of course not. So I move it like this, it comes to a halt. And when it comes to a halt, in this particular case, the frictional force becomes even zero. In this particular case, the frictional force has to balance out this spring force.